Hi and welcome to Query Plans and Operators. My name is John Snelson and I'm a Principal Engineer leading the Optic Engine team in MarkLogic. This talk is part one of 5 parts of the Optic Engine deep dive, and so if you're interested in the material that we cover today and you'd like to know more, do go and find those other parts on the website. First of all, to give you an overview of what the Optic Engine is. So the Optic Engine is responsible for executing all SQL queries, all SPARQL queries, and any Optic API queries that get executed against MarkLogic. You can see in this architecture diagram, the languages are there on the right hand side. And then moving left, you can see the execution engine that happens on the E node and the operations there, and then the network messages that transfer to the D node and result in parts of plans being executed on the D node, and also the indexes which are there resident with the data on those D nodes. Now when we execute one of these queries, first of all, we build a logical plan. That determines what should happen, but not how it's going to happen. It contains a tree of all the operators that need to be performed, but then we move into the stage where we optimize or determine the physical plan for that query. So the physical plan starts to fill in the how it's going to happen, what algorithms we're going to use, what order we're going to do that in. We'll go into more about how optimization works in part 2 of this deep dive, so do go and find that if you're more interested in that side of things. But when we have a physical plan, then we're ready to execute the plan. And today we're going to look at some of those physical plan operators and how they execute inside MarkLogic. So to reiterate on this, an example of a logical operator is an inner join. Okay, that we know what an inner join is, but there are many ways to execute that join. A hash join is a physical operator, and that physical operator implements the logical operator inner join. So a hash join tells us how to execute that operator. So again, the SQL parser, the SPARQL parser, and the Optic API builder, they all create logical operators, and then that gets passed to MarkLogic's optimizer, and that chooses the physical operators. And at the moment, there's no user choice about which physical operators are chosen, but that is something that we're looking at. When we have an optimized physical plan for a query, that is cached inside MarkLogic. And that is cached for a certain period of time, after which it's re-optimized. We do that because if the data is changing significantly in our database, the assumptions that we made when we optimized that query may have changed, and we need to re-optimize to check that we're still using the most efficient plan that there is in order to execute that query. So when we're executing these plans, some of these operations happen on the E node. In fact, most of them happen on the E node, but some of them also get transferred and happen on the D nodes. And since it's useful to be able to know the difference between those two, there's going to be a little circle that appears in the top left corner to tell you whether this operator is executing on the E node or on the D node. I won't necessarily say for each slide what's going on there, but you'll be able to see that and know where that operator can execute. In addition, there are various trace flags that you can set in MarkLogic to get it to produce useful output about what's being executed. And you'll see some of those plan outputs in my slides. If you want to see the same kind of output from your queries that I'm showing on the slides, you'll see these little trace flag grey boxes on the screen there, and they will tell you which which trace flag I've used to capture that output. But in summary, the optic plan trace flag gives you an understanding of the whole plan for the query, and usually most of that will execute on the E node. When portions of that are executed on the D node, you'll be able to see the message just before it gets sent to the D node, and that message is output using the optic execution trace flag. So when we look at our query plans, there are always leaf nodes in that query plan, and the leaf nodes are where the data comes from. So those leaf nodes, those index accesses, always happen on the D node. And the most obvious of those is the triple index accessor, which you can see right now. Now, there's a little box at the bottom of the slide there. That just tells you some of the details of the query that I executed in order to capture this part of the plan. What you can see happening here is there's some constraints on the subject and the predicate of this triple that we're looking up. We're also the optimizer is also chosen to access a permutation PSO. Now that's the way of describing the sort order that the parts of the triple are sorted by, and it's sorted first by predicate, second by subject, and third by object. So, I should say the triple index accessor also gets used for accessing columns individually, and often that might be because there's a constraint against that column, or we want the values in sorted order for some reason from that column. But when we're accessing tables in Optic, you may see a row accessor, and that row accessor is accessing entire rows from the triple index. It's a specialist operator that is able to do that more efficiently. You can see a few constraints against this particular row accessor. One of them is book ID equals trader 07. There is usually a range constraint against the rows. That range constraint normally tells the triple index access which table it's accessing. Those numbers equate to the correct table that we want to access. And in this case, we're accessing rows in a row-oriented fashion. So that's where the triple index uses a certain permutation where all the values for a single row are contiguous together in the triple index. An alternative is the column-oriented access, which the rows accessor will also do. With column-oriented access, we access each column individually, and that means that if we're skipping, if we projected out a number of the columns from that row, then it can be more efficient to use a column-based access. If you want to know more about how triple index access works, including the row accessor, you can go and have a look at part 5 of this deep dive, where we look at triple index queries and how they're executed. In addition to accessing tables and triples from the triple index, the Optic Engine can access range index information. In this case, it's called the lexicon accessor. And the lexicon accessor here can be seen accessing an element range index on col3_date. So we have a number of join operators in the Optic Engine that we support, including inner joins, left or right outer joins. In SPARQL that would be optional. Semi joins, so that would be exists or in. Anti joins, which are not exists, not in, and minus is a SPARQL operator that is an anti join. As well as full outer joins, intersections, and unions. Now, I'm not going to go into the ins and outs of every single one of those types of joins operators, but what we will do is we'll look at the main types of operator in the context of an inner join. So joins, you'll see at the top there, joins can happen both on the E node and on the D node. And when we push joins down to the D node, that's usually because we know we can answer that part of the query from a specific stand in a specific forest of the database. Usually that means there's a constraint based on a row ID or based on a fragment ID, and that allows us to be able to push down the join. So the most obvious join algorithm is a hash join, and that's something that a lot of people are familiar with. But let's just look at how the hash join works in MarkLogic. We have a convention in MarkLogic in the query plans that we output that the hash table is always made from the left-hand side of the join, the first operand in the join. So in this case, we've got a query here. You can see the SPARQL query equivalent at the bottom. But in this case, we're going to take that left-hand side and we're going to build a hash table where the hash value is mapped to the row from that left-hand side. And then after building that, and obviously that means reading the entire left-hand side into memory, we're then going to scan through the right-hand side. And as we scan through the right-hand side, we can read that out of the triple index in a streaming fashion, so that doesn't have to all be in memory at the same time. But as we stream each row, we look up in the hash table for the join condition. We find the row that it joins against, and we output the result, which is the joining of those two pieces of information. Here you can see query plan output for a hash join. The important part here is that you can see the attribute at the top of that document that says that it's a hash join. It's detailing the physical operator for this plan. So kind of an incremental version of the hash join is a scatter join. A scatter join uses what's called sideways information passing. So sideways information passing is where you take information from one side of the join and you use it to constrain the execution of the other side of the join. And the object here is to make the part of the side of the join that receives the information more efficient by being able to do less work because it knows what values it needs to produce that will actually result in a join. So for a scatter join, we proceed as normal. We look at the left-hand side and we build a hash table there. But whilst we're building that hash table, we also keep a track of the unique values from that left-hand side that will produce a positive join result. And we take those unique values, we call those scatter values, and we pass those into the execution of the right-hand side. And they restrict the values that the right-hand side needs to return. So then we still stream the right-hand side. It's just that usually there'll be less results on the right-hand side that we need to stream. And as we stream those results, we still look them up in the hash table on the left-hand side, which then produces the result in the normal way from the normal hash algorithm. An incremental step further to a scatter join is a bloom join, and a bloom join also uses sideways information passing. But this time, when we're building our hash table, we actually build a bloom filter. A bloom filter is a probabilistic data structure. If you're interested, you can go and look it up on Wikipedia. But it provides a yes, no, in or out kind of answer for every value. But it uses a fixed amount of memory. So in the case where a scatter join would produce a list of values that was way too big to send over to the D node, a bloom join can come to the rescue and produce something similar, not quite as efficient, but similar in a small fixed amount of memory. So we build that bloom filter, we pass it over to the execution of the right hand side, and when we're streaming the right hand side back again, we check to see if the result is needed in the bloom filter at the relevant points, and therefore we can reduce the execution that we do on the right hand side. So for a completely different join algorithm, the sort merge join first takes its two operands, the left and the right hand side, and it makes sure that they are sorted. Now it may do that by implementing a brute force sort, a quick sort, bringing them all into memory and sorting them manually, or the optimizer is actually pretty good at arranging for results to come back already sorted by a particular column. It does that using the permutations and the triple index, and it does that using careful bookkeeping as well. And if you're interested in that, part 2 of the deep dive about the optimizer will help you to understand how that happens. But having got the two sides sorted based on the join condition, we then stream the left hand side and the right hand side, and we kind of zip them together. We match up the values that match and produce the result of that sort merge join. Now if we can arrange for the sort orders to already be provided from the indexes, then this is very efficient and we don't have to buffer anything into memory in order to do that kind of join. So that can be quite useful for the optimizer to use to minimize memory usage. And lastly, we've got the broadcast join. So the broadcast join is a hash join with a difference. It actually executes not solely on the E node, not solely on the D node, but actually on both the E node and the D node. So let's look at what happens and where that happens. So first of all, the left hand side is red and we build a hash table, and we do that on the E node. On the E node is where all of the information comes back together and is complete. So that makes sense that we build the hash table there. But what we do is we then take that hash table and we ship the entire hash table over the network to the D node, so that when we stream the right hand side and we're streaming it on the D node, we can perform that hash lookup on the D node before we send results back to the E node. So this kind of join can be quite useful in data warehousing situations, where you might have a large central table and you might have smaller dimension tables. And those smaller tables can result in small hash join tables, and therefore we're not sending an awful lot of information over the network when we send the hash join table there. But it may also allow us to push down more operations to the D node on top of that broadcast join. So we might be able to push down grouping. We might be able to push down more filter execution or things like that, because the broadcast join has pushed that information down to the D node and it's available on the D node there. So we also obviously do sorting. If you have an order by, sorting can happen on the E node or the D node. And you'll notice that this query plan, in the query plan it says num sorted equals 1, that attribute in green at the top there. So that actually tells me that this order by operator has managed to arrange for the query inside it, for its operands to return in sorted order already. So it doesn't need to perform any operations in order to do the sort. That it gets the sort for free. Where you have more than one order by column, in those circumstances you may see num sorted equals 1, but there are 2 columns to sort by, in which case we'll do a partial order. So the partial order works by first grouping on the columns which are already sorted, and then within those groups we do a brute force sort for the next columns, the ones that aren't yet sorted on. And that results in a lot less memory usage, and it's a lot quicker as well. So that can be a pretty useful technique. When we do those brute force sorts, also, obviously that involves bringing all of the rows into memory, and then we'll execute that with a quick sort algorithm, the industry standard, a kind of fast sort algorithm. So you'll also see, not just for order by, but for any other operator that needs sorting, you'll see those num sorted attributes. And if you look for those, you can see whether it's going to do a brute force in-memory sort, or whether it's actually having the sort orders provided from the indexes already. When we do grouping and aggregate calculations, that can happen on the E node or the D node, and actually pushing it down to the D node means that it's executed very much in parallel on every stand, so it's going to be a lot quicker doing it that way. You'll notice at the top of the query plan output there, it says that this is a sort based group, so this is working based on a sort order, and in this case num sorted equals 1. So the sort order is provided by its operand already and doesn't need to actually do that brute force sort. Other type of grouping operators are the hash-based grouping operator. So when we're using a sort-based grouping operator, all of the group's rows are together, sorted together, and so as we stream those results in sorted order, we can take a group at a time, find the group boundary, and calculate the aggregate on all of those rows altogether. If we're using the hash-based grouping algorithm, then as the rows come in, they're not in any order, so we dispatch each row to the relevant group by working out its grouping key based on a hash code and sending it to those groups to be counted, each one. So if we are performing a D node grouping, if we're pushing this down to the D node, we can't actually complete the grouping algorithm until all of the information from all of the D nodes has come back to the E node. But as they're coming back from the E node, we perform a reducer step, as in map reduce, in order to combine those and create the final grouping aggregates. And if you're more interested in how the reducing works in this situation and others, when we're pulling information and combining it from multiple D nodes on the E node, then we're going to talk about that in part 5, which is the triple index queries part. Now, when we do filtering, like this would be a where clause or a filter clause in SPARQL, there's two kind of ways that you'll see that in the query plan. In this instance, the query plan that we're looking at here, we haven't been able to push down this filter expression. So this filter expression, you can see the query at the bottom here, but this is the second part of the filter expression, the num shares modulo 100. You can see that reflected in the query plan there. And that will execute on the E node. When we execute filters on the D node, you'll see the filter expressions become part of index accessors or part of a join operator. So you can see it here highlighted in green. It's actually part of the triple index accessor in this case. And that is the filter that says stock symbol equals PFLT. And we'll talk more about pushing down filters and which filters can and can't be pushed down in part 2, where we talk about how we optimize queries. There are a number of other different operators that are kind of less well known and less well used in the Optic Engine, and all of these execute on the E node. So just a few of these are the bind operator. So that's responsible for bind expressions and for select expressions. Any kind of expression, scalar expression that needs to be evaluated will use a bind. We've also got a projection operator and a distinct operator. There's the limit offset operator. Works together. And then there's a few SPARQL only operators. There's the one or more operator, which is it corresponds to SPARQL property path plus, the plus operator. And there's a 0 or 1 operator, which is again SPARQL property paths, the question mark operator. So that's for transitive closures. And there's also a values operator, which is used for values sections, kind of literal tables that can be written in SPARQL queries. Now we've been looking at some of the XML trace output for all of this information, and you'll see that in your logs if you use the trace plans, or if you ask for a query plan, you'll get that back and it'll look like the slides we've just been looking at. And if you find that it's hard to understand those query plans and make sense of them, then you won't be alone. My team also found that that was difficult. And so I ended up writing this query plan viewer. I've put that on, the code for that on GitHub, and it's a liberal open source license. It's basically a MarkLogic app server that you would paste that query plan into, and it gives you an HTML view that you can zoom into. You can look around, and if you hover over, you can get more information on each operator. So the URL for that is on the slide. Do go and check it out, because it makes it a lot simpler to see this full structure of the query plan and how it's all fitting together and working together. So to summarize what we've learned today, so we looked at how the optimizer creates a physical plan from the logical plan, and we've looked at how execution happens both on the E node and on the D node, depending on the operator and the query plan. We've looked at the various types of join algorithms, and in particular we looked at sideways information passing, which is the scatter join and the bloom join, where we're using the left-hand side to constrain the execution of the right-hand side. We looked at sorting and how we can tell whether brute force sort is necessary. We looked at hash and sort based grouping, and hopefully this has given us a foundation for understanding efficient query execution. And we'll come back to a lot of this knowledge in part 3, where we look at diagnosing potential problems in query execution, and how we can understand what's going on and might be going wrong in that. Thank you for your time.